Good morning, everybody. Welcome to our plenary. So I'm Alexandra Kurfali. I'm the program manager at EuroHPC, taking care of our CHIPS projects. And I want to welcome you to our plenary called Future Technologies Powering the Current and Upcoming European Supercomputing Infrastructure, the Road to European Sovereignty. So we have prepared a session that will showcase the current status of the CHIPS projects and what we have planned for the road ahead. So we will guide you in the road that we have designed for this plenary, starting with a keynote address by the European pilot project that will showcase the current status and how it connects with current and future projects. Then we will have a panel of experts that will be discussing where we are now and where we want to go ahead. And then we will close with a keynote by ETP for HPC about the future. So please keep all questions at the end because we will do a joint Q&A session. And let's start. So with this mark, I would like to ask Carlos Puchol to come on stage. So Carlos graduated in computer science, specializing in AI and deep learning. He holds an MSc and PhD from University of Texas at Austin. He has a distinguished career as researcher at Bell Labs and power management architect at Transmeter, NVIDIA, and other companies. And he has been focused on maximizing system efficiency and low power design. Carlos has been an avid open source contributor and was the first person to boot the x86-64 Linux kernel, collaborated with Linus Torvalds at Transmeta. With over 20 publications and 7 patents, his work spans internet telephony, CPU, virtualization, and chip architecture. So the floor is yours.
Thank you, Alexia. Good morning, everyone. I'm Carlos from the Barcelona Supercomputing Center, where I've had the pleasure of helping guide and coordinate this project called the European Pilot, also known as EU Pilot. I first wanted to begin by giving you an idea of the size of the project. It's about 30 million euros in budget, and you can see the distribution of the partners on the screen. There's 19 partners, and the expertise really spans from chip design to chip implementation to board design, systems, even deployment on liquid immersion tanks. And that's on the hardware side. On the software side, the project also goes from operating systems all the way to applications, going through libraries and so forth. So going into a little bit more detail, the objective of the project is really to demonstrate a pre-exascale accelerator platform. Now, to do that, really, it can be broken down into first building it. It really is a project that spans a huge amount of expertise, and doing so with maximization of the European technologies and assets. The other thing that the project wants to do is really to stimulate the collaboration between partners here in Europe and to foster and enable future supercomputing projects. Another thing that the project has as a goal is to use open technologies like RISC-V, as well as the Open Compute Project, OCP, set of standards that help open up the market for the supercomputing world. In addition, of course, we use Linux, OpenMP, MPI, all the usual suspects. Last but not least, it's very important to do these technologies such as they're efficient and sustainable. So ultimately, what the project really pursues is to strengthen the European digital autonomy as well as the HPC and AI supply chain. Now, to describe the project and the wide range of things that we're going to have, we have a video. But before the video, I will tell you that EU Pilot really leverages key software and hardware technologies from the European Processor Initiative project that many of you are probably more familiar with. The project has really two major tracks. One is for accelerators, and the other one is for the general purpose processor. So EU Pilot really leverages the accelerator track of API. And what EU Pilot does is, in addition of collaborating with user communities like COEs, as well as a project called UPEX, we really try to make these as stepping stones towards bigger and better projects like there. Now, you can actually find us on as soon as you get out. On the left, there's the posters for EU Pilot and UPEX. So you're welcome to stop by if you have any more questions. Now, we have a video that will show, a very short video that shows the overview.
Can you imagine a future where the entire semiconductor value chain is provided by European sources? The European Pilot project is a key project towards realizing this goal. World-class competitiveness, leadership, and self-reliance in industry and science are now more important than ever in Europe. Bringing a new level of high-performance computing, data analytics, and maximizing the use of European technology, EU Pilot makes use of open source and open standards to create an integrated software and hardware system. From microchip designs to the systems incorporating them to deployment in data centers, EU Pilot pushes the envelope in high performance and energy efficiency. With a streamlined software stack, EU Pilot systems are being designed to accelerate computationally intensive applications in the fields of molecular and climate modeling, genomics, biomechanics, geophysics, and many other domains. EU Pilot is creating two complementary RISC-V accelerator chips designed, implemented, and deployed in Europe. One for vector-driven tasks like scientific computing, called VEC, and another for data analytics, AI, and machine learning applications, called MLS. Each VEC accelerator contains an array of compute tiles, and each tile contains a CPU and a vector processing unit. The MLS accelerator contains clusters of a larger number of small yet efficient cores specialized on computations most frequently used in data analytics, machine learning, and AI. These chips, coupled with memory chips, form accelerator modules, and multiple modules are hosted on a baseboard within a chassis to form an accelerator system. Each accelerator system is then paired with a host server and is immersed into a liquid cooling tank which can hold up to a dozen hosts and accelerators. Gone are the days of server racks taking up an inordinate amount of power. Now, multiple liquid-cooled tanks can be deployed in a data center for a large integration of compute capacity and density at unparalleled levels of power and cooling efficiency. The European Pilot, contributing to a sustainable exascale supply ecosystem in Europe and ensuring European digital autonomy in this field.
All right. Thank you very much. Let me describe now how the project is organized. As you've seen in the video, the project spans a very large range of expertise. So the project has three main work streams. One is hardware, the other one is software, the other one is systems. In terms of hardware, we leverage the work that has been done taping out a prior accelerator in 22 nanometers. And in this project, as you've seen in the video, we're going to tape out two chips, one in 12 nanometers, the other one in 7 nanometers. In addition, we also have taped a test chip to check out the technology node, which you can see over here. This is the test chip. And we are about to tape out the other two chips this summer. In terms of software, really, the project doesn't focus on running many applications. Rather, it focuses on key applications on the HPC side and on the application side. And so all that work involves porting tool chains and libraries, frameworks, and so forth that can run on RISC-V, and in some cases, either manually or automatically, they can run optimized versions, or doing vectorization automatically or manually. Now, in terms of systems, the project then has to put all that hardware and software into boards, which we'll see in a moment, and deploy those systems into racks in a data center environment. And the project also calls for doing liquid immersion cooling for these systems. That basically reduces environmental impact and also enables higher workloads. Now, ultimately, really what the project wants to do is to deploy an accelerator demonstrator in a data center-like environment. So the idea is to improve the TRL over time. In this case, we'll deploy at the Mare Nostrum 5 environment. Ideally, also, this project wants to become a software development vehicle and leverage all that expertise towards larger supercomputer projects that come later. Now, just recapping, so that we have 2 chips. Either one of them goes into the so-called modules that you can see over here. Those modules get put together on baseboards. The modules, we have a small mock-up of what those modules look like. So you can see this is the size, the chip, the size. This is the chip and the memories that go on it. And then those baseboards, they get put together on a chassis, which then it gets paired with a host, and the host gets deployed into a liquid immersion pod. Now, looking a little bit about the module, a module contains 1 chip and 4 LPDDR memory interfaces. It contains 6 chip-to-chip interfaces, which helps put together multiple of these modules with a very high-speed interconnection network, and they can, a coherent network, which actually means that they can share memory and so forth. And in addition, it has a CXL interface that can talk to the host. So looking at the architecture of the system, each one of these boards is one of these EAMs, EU Pilot Accelerator modules, and they have a chip-to-chip interconnection network, which then gets connected to a host through a high-speed CXL interface. Now, I know this slide has a lot of content, but I just wanted to focus that there's really 2 stacks, and they share some parts of the stack. On the right-hand side, you can see AI, and it's in green. You can see AI, some of the tasks that are specific to AI. And on the left-hand side, you see the ones in red that are specific to HPC. But you can see that on the accelerator and MLS sides, they really do share quite a bit of work put together. So that's kind of like the overview of the software. Now, going a little bit of where we are, the projects and on the track of accelerators have been doing essentially 1 tape out a year up to now. And you can see that's the test chip over here. And then you can see APAC processor prior. You'll hear a little bit more about that in a moment. Then this is where we are. And then we have 2 tape outs simultaneously this summer. One at Global Foundries with 12 nanometer technology, and then one at TSMC with 7 nanometer technology. Now here's a quick, literally an update of the chip die as of last week. It's about 7.8 millimeters on one side and 7.7 on the other side. These 2 rows of 4 are vector units and CPUs. And so the chip contains 8 tiles, each tile containing 1 RISC-V core, and each core has a tightly coupled vector processing unit on it. In addition, there's 2 memory interfaces, LPDDR memory interfaces on each side. And as I mentioned, there's 6 chip-to-chip link interconnects, which connect the chips in a very homogeneous way. This block here at the bottom is the CXL PCI Express 5 module that connects to hosts. And then this tiny little block over here is the controller of the chip, the one that operates and boots and resets the chip and does all the right things. It actually contains a tiny little RISC-V, open source RISC-V chip that acts as controller. That said, let's talk about peak performance projections. We expect basically on the VEC side with a budget that allows for an area of around 59 millimeters square, that running at a target of about 1 gigahertz, we expect 216 gigaflops per chip running 64-bit ops. When put together in a group of 8, they could reach about 1.6 teraflops per system. And in terms of MLS, with an area budget of about 20 millimeters square in 7 nanometers, and running also roughly at around 1 gigahertz speed, we expect to have 768 gigaflops per chip in 8-bit operations. And so that's essentially a very quick overview of the project. And like I said, if you find us up here, feel free to ask questions. And also the poster for EuPEX and EuPilot are here as soon as you left on the left side. And I think that's all. Thank you.
Thank you, Carlos. And please stay close for the questions at the end. So let's get back to it. So as we said, EuPilot is connected with the EPI project. So as Carlos presented before, it is connected with the EPAC accelerator, and currently we have the EPAC accelerator being demonstrated at the demo lab exactly as you exit. So I will provide some sort of teaser of what you should expect at the demo lab, and we invite you after this plenary to visit the lab. So let's get to it. So the team has prepared a demonstration of what this accelerator can do. So it is, since we are moving towards heterogeneous architectures, we are basically start to offload computationally intensive tasks. And here you can see that the team set up YOLO, that is an image and video recognition, object recognition that use deep neural networks to recognize on real-time actually objects that you see. And here, as you see on your screen, here this runs in scalar, so natively without any acceleration. And you see that the object detection takes more or less a couple of seconds. And this is without any acceleration. And here, the computationally intensive part is a bit more than 2 seconds. And this is running actually on the accelerator, and it is connected with a host PC that is doing the rendering. So the inference is offloaded to the accelerator. So then the team has kicked off the vector accelerator. So we have some vector operations happening now. And as you see already, the compute time is cut in less than half. So we have detection in 1 second. And if you notice, the compute time is 0.6 to 0.7 seconds. And then at the end, they do also a few more optimizations. And then they cut the compute time even more. And here you see that they put it down on 0.3 seconds. And so from this, you can see that already we have accelerators that work. And this is the path ahead and towards the DARE project. And with this note, I would like to invite our panelists to the stage. So for the next part of this plenary, we have a panel with top experts and top contributors of in EuroHPC projects. So we have Dr. Teresa Cervero Garcia from BSc. We have Dr. Gianna Paulin from Axelera. We have Dr. Lilia Zaourar from CEA. We have Professor Estela Suarez from SiPEARL and Professor Cristina Silvano from Politecnico di Milano. So please welcome them. And please introduce yourselves, where you work, your affiliation, your area of expertise, and your favorite EuroHPC project.
Should I start?
Yes.
Oh, okay. My name is Teresa Cervero. I'm working at Barcelona Supercomputing Center as part of the computer science department. I have a background in telecommunication engineering, reconfigurable hardware architectures, and now I'm working on providing support, technical support on hardware development for accelerators on RISC-V. I was involved on the ME projects, on the technical coordination, and now I'm working more on the co-design for moving and optimizing applications, or providing support on optimizing applications on RISC-V platforms. And there on the community side, I'm also working, involved in RISC-V community as vice chair of the special interest group on HPC.
Thank you. Gianna.
So hi everyone, my name is Gianna Paulin. I'm probably the youngest here, so I finished my PhD a little bit more than 1 year ago at ETH Zurich in Switzerland with Professor Luca Benini. Some of you might have heard of my PhD project, which made the news roughly 2 years ago. So we had the Okami project with 2 compute chiplets, 2 HBMs in a 2.5D integrated package with a silicon interposer. And during my PhD, I basically led this project. And now, since 1 year, I'm at Axelera in the computing architecture team, helping to build the new generations of AI accelerators. And yeah, I was responsible for setting up the DARE EU project from Axelera's side. So I guess that's also my favorite EuroHPC project right now.
Lilia.
Good morning, everyone. I'm Lilia Zaourar. I'm expert in co-design of digital architectures, mainly HPC and AI ones. My main motto and expertise is on optimization techniques and strategies for modelization, simulation, and design space exploration across hardware and software. My main let's say, motto is to find, and obsession is to find the best compromise across various key performance indicators. I have been working on various EuroHPC projects. My favorite one is European Processor Initiatives, where we try to find the best, once again, compromise for HPC for the RIA chip. And more recently, I have been involved in Net4Exa, which is the new one, and I'm sure it will take also a lot of energy and expertise, but I'm very happy for that.
So, my name is Estela Suarez. I am currently at SiPEARL. I've been for 15 years at the ULI Supercomputing Center, co-leading with a colleague a unit that is responsible for novel system architectures. So that's basically my expertise in HPC, is looking into how different kinds of processor technology, network technology, memories need to be combined to build a system that is suitable for a wide range of applications. So as a HPC center with a lot of applications and different users, you need to make them more or less reasonable, all of them reasonably happy. Within SiPEARL, I'm also responsible for system architecture. So again, thinking about how to combine the CPU, the RIA CPU, with other kinds of accelerators, maybe develop some of them, hopefully in Europe, and how to build with these large HPC systems. Yeah.
Morning, everyone. This is Cristina Silvano from Politecnico di Milano. I'm a teacher in computer architecture, and I'm also expert in energy-efficient computer architectures, EDA tools, especially design space exploration tools, and most recently, accelerators for deep learning. I'm also one of the promoters of the European Master Initiative for HPC, and especially we designed a master program at Politecnico di Milano for HPC students, and I was also a project coordinator of 3 European projects. The last one on HPC is Antarex project in collaboration with Cineca and IT for Innovations.
Thank you. So let's start. So as probably you know, EuroHPC is aiming to be one of the key driving forces behind efforts and initiatives in Europe to design the new family of processors and accelerators. So, Estela, how do you think that RISC-V and ARM contribute to Europe's push for technological sovereignty in HPC?
Well, To become sovereign in Europe, I think what we need first is to be able to have homegrown processor development for high-end users, so for HPC, for AI. And RISC-V and ARM are the two instruction set architectures we have right now available that allows European industry to develop a product for these or other markets. So in a sense, it's a vehicle, it's a basis to build our own technologies in our continent.
Okay, thank you. And Teresa, do you think that we are on track to reduce the dependency on non-European technologies?
Okay, is this a tricky question? No, I mean, I think we are on track. I mean, we have we are developing technology. I think a very important piece here is also the workforce and the know-how that we are generating on all these processes with all these initiatives. Because basically if we want to design, build, and fabricate, we need people to do that. So I think we are gaining a lot of expertise. And also with RISC-V, for example, I think being an open standard helps a lot of to being creative and innovate. So I think we are on track. We are designing, we are developing. The fabrication perhaps is the weakness at this point. But we are developing the expertise on hardware, also on software. So I think we are doing good.
Okay, good. Thank you. So, of course, between RISC-V and ARM architectures, we have some differences compared to the traditional x86-based solution in terms of scalability, power efficiency, and performance on specifically for HPC workloads. What do you think about that, Cristina? How close are we?
And currently, I think still dominated the HPC microprocessor market by big processors from Intel, AMD, and NVIDIA, especially for accelerating by using very powerful GPUs. But they are still approaching and entering the market, I believe, in a time frame of 5-10 years, the RISC-V based or open license approach, and there are still some very interesting commercial solutions provided by ARM on several cloud-based systems and already commercialized. So you are keeping the pace to try to be on track on this kind of very important technology for Europe, especially because we need to exploit the link with the AI market.
Okay, and Lilia, is this also your opinion as well from CA?
Yeah, for sure. Traditional architectures like x86 have been widely used, and various, let's say, general purpose computing. Nowadays, the ARM architectures is gaining a lot of interest. It has been already deployed in big major HPC systems like the Fugaku. It's gaining a lot of interest also in the Graviton 3, and we hope it will continue on European sovereignty. On the other side, for sure, RISC-V OpenESA is also very promising, but it still needs a little bit of development to be deployed as the previous ones.
Yeah, it's a bit of more long-term solution. Yes, thank you. And let's talk now a bit about software. So, Teresa, what do you think are the biggest software challenges in adopting RISC-V architectures for HPC?
I think we have already mentioned that, so it's the lack of maturity.
Yeah.
I think the natural path that we are following is supporting libraries and workloads, runtimes. But I think that the most challenging piece here is to understand how to take advantage of, for example, how to exploit the custom instructions to do things in a different way. And for these, I think compiler and toolchains make a very, very important role here. So we have to pay much more attention because this interface to understand the underlying architecture, all the features, to explore that, but in a way that also users and developers doesn't have to struggle too much to take the best of that. I think that are the kind of things that we need to work more, and the challenges, basically.
And another challenge that we discussed in RISC-V summits is the risk of fragmentation. So is it an actual risk? What do you think?
I don't think it's a risk. From a point of view of the possibility of having explorations and doing things in a different way, it's freedom. It's true that you can test different things, but it doesn't mean that in the end it's going to be part of the standard. So you have the freedom to test and then promote that as part of the standard. The nice thing of RISC-V is it's a community-driven standard, so you can participate, directly involve, and push for that. And also, I don't think it's fragmentation, because now we have this definition on extensions, that we are working on profiles. We have the RVA 23, for example, so which creates this agreement between software developers and hardware developers, so they have the baseline, the mandatory extensions that have to be there, and then the freedom to add new things there. And then we are moving to platforms too, which also help us to identify the key pieces that need to be considered for creating the next infrastructures, not only the accelerator, but at system level. So I don't think fragmentation is a big issue.
That's actually quite reassuring, thanks. Okay, and let's talk a bit about co-design, if you don't mind. So, Lilia, how critical is hardware-software co-design for the success of RISC-V, but also of ARM in European supercomputers? Are there any concrete examples of successful co-design efforts?
Yeah, for sure, co-design is a main piece element for both hardware and software development. It takes time.
Can you put your...
sorry,
okay, yes.
Is it better? Okay. I was saying that for sure co-design is one of the main pieces of the success of both hardware and software. One success story has been the Mont Blanc and API history along for the ARM development. So it takes, as I said, sometimes, but it's also very exciting since we have various expertise, various discussions with various colleagues and the partners. So it's really, let's say, the main piece to go through it. And for sure, for RISC-V, it's beginning. I hope it will be also a success as for the ARM architectures. But for me, also the main piece around the co-design is the tools. We need to have these tools going, usually named as EDA, Electronic Design Automation Tools, but it's always, how to say, always an adventure, let's say, to start new tools, to maintain them, and to gain also expertise on that.
Absolutely, thank you.
Can I add something
yes,
about
please.
this? I fully agree with Lilia that the co-design is fundamental, especially for customization of AI-based solutions. And there is a lot of research on, for example, mapping in time and space, on deep learning kernels. And I think this is fundamental approach in order to better exploit what we have in terms of resources in the architecture and the memory hierarchy in order to implement data reuse as much as possible, and this is fundamental, for example, for getting the best in terms of energy efficiency. That for accelerators is measured in terms of terafloating point operations per second per watt. This is the fundamental metric we have to keep as our main goal.
Yes.
And if I might jump in, I think it's very, very important, the co-design, and I think we are learning a lot from all the projects that we are participating in Europe. And we cannot forget about also the application layers, because we are talking about hardware and software co-design, which is very specialized with researchers, experts in hardware and software. But we need to understand what the users or the needs, or the KPIs, and then translate those in something that software people and hardware people can, look for. So I think we have to extend the conversations with the application users to understand what their real needs, because perhaps we want to accelerate, I don't know, some metrics, and then perhaps for them are not very, very important. So we have to continue those kind of discussions.
Cross-layer metrics then, basically. Yes.
Yeah, you're all right, Teresa. The end users are very important, and also important to include them from the beginning, to express what are the real objectives, how to really evaluate the metrics to be really efficient at the end of the day. Yeah, sure.
Okay. Perfect. And we will move on now to the big buzzword of this year, I think. We'll talk a bit about AI accelerators and HPC synergy. So Gianna, AI-driven workloads are playing an increasing role in HPC, if anybody has noticed. How well do RISC-V architectures support AI acceleration compared to traditional GPUs or GPUs?
Well, RISC-V is open. It's designed to be extensible, and one of the biggest benefits, which I also see as a company building hardware accelerators, is that we can own the IP. So we have really full control. We can optimize the integration into the entire SoC, into the system. And of course, it might lack a little bit of software maturity right now, but in the end, for a company to create value, it's important to own something, and that's where RISC-V is great. Yeah.
Okay, thank you. But I will follow up a bit on AI accelerators.
Sure.
So now, with the DERT project, Europe is developing custom AI accelerators based on RISC-V. Of course, it started through EPI, and now we have this significant investment towards DER. And here, at the middle of this, a shining example is Axelera. What are the architectural innovations in these accelerators that will be happening at DER? Can you give us like a teaser what we should expect?
Sure. So we have basically two key technologies which we exploit, one of which we mentioned already, RISC-V, and the other is digital in-memory compute, which is really a full custom design on a transistor level, handcrafted. And in-memory compute means you can keep the weights quasi-static locally and reduce and optimize the data transfers to the main memory. And second of all, since it's really a handcrafted design, you can really push the energy efficiency to the limit within the digital realm, let's say, or at least we focus on the digital in-memory compute arrays. And yeah, I think RISC-V, also to maybe come back in a little bit, Axelera is really focusing on building accelerators for inference. So compared to GPUs, which are currently serving like many needs, so they try to serve high precision computing of HPC, of AI training, and also more and more on AI inference, because many market prognoses actually say that inference deployment will be a much bigger market than training in the long run. And so that's where we try to position ourselves. And this really gives the option to customize your hardware way more for the use case. So you can use reduced precision, quantization, and you can really optimize your data flow architecture to your applications. So you have really a lot of co-design. So it's like, if you look at the HPC domain, I think yesterday in the application session there was a lot of discussion of whether or how much co-design has actually influenced real hardware products. And I think with AI we have an opportunity to start from scratch, see what are the real AI workloads which help HPC applications, but also all the other needs from other market segments. And yeah, that's what we do. We highly customize our architecture for inference acceleration and exploit, as said, RISC-V and digital in-memory compute.
Thank you. I'm looking forward to see how this will be integrated in there. So, what are the biggest challenges in optimizing AI workloads in European projects? Estela, can you give us some overview from your experience?
Well, I think that not only for AI, but in general for applications, the biggest challenge is always to deliver also the software stack on top of these new instruction set architectures, these new architectures, either they are general purpose or accelerators, that helps the workloads to port from what they are used to run on, which is x86 or GPUs, into the new device. The one thing that one could argue on the AI side might be a bit helping is that most of the applications run on top of some frameworks. So if you are able to adapt the framework, the back end of the framework to support the new hardware that we have now in Europe, then you can more or less automatically make sure that the applications that run on top of those frameworks will optimally run on the hardware. So there is this abstraction layer that might help which is much more harder in HPC traditional applications that tend to run on bare hardware. So there are tons and tons of different codes that need to be ported individually. Yeah. So a lot of software is, I think the software is the key element here to help of the adoption of these new devices.
Okay, okay, thank you. And Teresa, if you can add a bit from the RISC-V side, so are we making progress in par with ARM in software hardware co-design, or it's, I mean, of course, it takes more time, we know, but how are we going?
Yeah, I think we are making progress, and actually one of the discussions we are having in the SIG and HPC, for example, is to analyze this gap analysis on HPC, where we are, where are the bottlenecks, where are the missing pieces that we are having. We are starting from, we are having two approaches. One is bottom-up, so for an application, trying to identify one killing application and trying to go down to the hardware, and also on the other side, we are also following a bottom-up approach to understanding what are the key pieces that we are having and the missing ones, and trying to, you know, to match in the middle and to meet in the middle and see. There are still things, as I said in the beginning, we are making progress, we are porting libraries, we are making efforts there, and we are growing and advancing. For example, on AI now, we are having these discussions on attached or integrated matrix extension, this kind of discussion that can help also to optimize the next generation of accelerators. I think it's really interesting, and we are also being pushed by the community, and this community is research centers, enterprises, I mean companies, or academia, individuals, and I think it's very exciting because we are moving together in the same direction.
Yeah. And it's a very motivated and active community as well. I've seen the vibe. So let's talk a bit about legacy codes. So it's a very big discussion in Europe that we have a lot of legacy codes that cannot or doesn't make any sense to port them into accelerators. So Lilia, how will AI accelerators help drive breakthroughs in scientific HPC workloads? For example, with climate modeling, drug discovery, quantum simulations. So does this make any sense to move towards AI acceleration, or should we keep business as usual?
Yeah. Once again, I think we have to think about compromise.
Okay.
not going through new, let's say, new things, but we need to go through new things, but don't forget also traditional and useful technologies and techniques. So for sure, AI workload will help to go through AI science, let's say, and climate, for example, is really a good example. It's always be there and will always be there. So we need to find a good compromise between AI workload and traditional HPC workload, and climate simulation and exploration. It's a good example. So I think we need to think differently nowadays, given these new architectures and the new opportunities, but also keep in mind traditional techniques. Yes. I'm not sure I...
Yes, no, this covers my question. Thank you. And now, okay, so that's where we are now, but let's talk a bit about the future. So one possible path that we see going towards the future is putting a lot of effort on interconnects and memory technologies. So Lilia, since we're still speaking, what innovation in interconnects, like for example for chiplets, optical networks, and memory hierarchies, will shape future European supercomputers, let's say 5 or 10 years?
Yeah, first of all, in terms of chiplet, I think it's a good opportunity because chiplet enhance modularity and will allow heterogeneous computing. As we said, HPC, IA are part of the game, and we need different workload, different software, and chiplet is really promising in that term. However, communication is an issue, as you mentioned. And I think new technologies like optical interconnect, photonics is really promising to help find once again the best compromise in terms of performance, power consumption, and of course, enhanced latency, which is a key element for exascale computing.
Yeah. And Cristina or Estela, would you like to add something?
Yeah, I agree that chiplet is the most interesting options nowadays, and more in general, I think interconnect is playing a fundamental role, especially because of, if you look at the energy cost, it is very dependent, it is very highly dependent on the communication between processors and the processor and the memory hierarchy, where it spend a lot of energy efficiency. So if you want to sell very important results in terms of energy efficiency of our solutions, I think we need to insist about evaluating different interconnection technologies based on chiplets or optical networks and whatever, because they are really fundamental in this overall, especially for customization, but at the same time keeping an eye on the standardization of the interconnection.
Okay, thank you. Estela, do you need to?
Yeah, well, on top of energy efficiency, I think also memory bandwidth is an important element. So the network on chip is a key element on the design of a processor to make sure that you get access, quick access to caches, to memory and everything else. So you really need to have a very good balanced design in the chip, not only on the processing side, on the memory hierarchy, on the net interconnect, and of course also then at system level when you want to scale up to the full machine. So certainly, it's the thing that connects everything.
Yeah. So everybody agrees. Okay.
Yeah, we really need to see the whole picture. Yeah.
Exactly.
As you said, from the chip to the system on chip to the chassis and all the rack. And the interconnect is always a problem, but also a solution to deal with all these different levels.
Okay, thank you. And let's discuss a bit more about energy efficiency and sustainability. Power efficiency is a key challenge for exascale and post-exascale computing. So how do you think RISC-V and ARM contribute to Europe's mandate for energy-efficient systems and energy-efficient supercomputers? And Teresa, Estela, actually, whoever wants, everybody's an expert on energy efficiency.
So, well, I can start. I mean, to be honest, neither ARM nor RISC-V by themselves will solve the problem of energy efficiency. They are just an instruction set architectures that allow you to design a processor that hopefully is targeted for energy efficiency. So it's not the kind of this, Saint Grial, whatever you call this. So there are many, many different aspects that contribute to energy efficiency. You can argue that both ARM and RISC-V have a bit of an advantage because of less legacy. They have less legacy than the x86. But at the end, energy efficiency comes from the process that you use for manufacturing. So are you at 12 nanometers, are you at 7 nanometers, are you at 3 nanometers? It comes from how do you interface all the components within the chip, where do you lose, where do you need to do unnecessary data movement between across the components that leave you to lose energy. So it's a very, very complex issue. And it's not only there, it's also thinking about at system level, how do you orchestrate all these components? So how often are they idle? How much they consume when they are idle? How can you make more dynamic and more adjusting the operations of your system according to the usage that it has? It's again, it's one of these problems that you cannot attack only in one direction. So you have to look into from the processor level to the interconnect to the system level, hardware and software sides.
Yeah, I think also from, as Estela has mentioned, so it's a complex problem. I think also the software stack, again, it's a key piece here. Now we are working on, most of the time, on static schedulers, for example, and we are using the compiler to analyze the data. But I think with these demands of computation and all these different working contexts, we need to move on dynamic orchestration and also giving more powerful to the data that is managed from the compiler. So I think we need to pay attention on that. Of course, we need to reduce the amount of data that we are moving through the system because that's energy, of course. We need to process data faster and closer to memory if possible, again, to reduce this data movement. but I don't think there is a magic solution that say, oh, you have to do this just to optimize the whole system, because it also depends on the application. So we need to also understand what are the kind of application or the kind of systems that we want, what kind of problems do we want to solve with those systems. It's very general. We want to tackle this kind of specific things and then optimize for those. Or we want something very general that can be, you know, getting the best or the better, the optimized solutions and efficiency.
Let me say also that you need to keep an eye also on the fact that you have a wide spectrum of energy efficiency solutions, and RISC-V, being an open hardware architecture, opens up a large spectrum of customizations. Each one could be for maximizing throughput, but at the same time, we can take a look at the cost. So another important metric is the cost over performance, and this is open up a wide scenario where also the cost could be a valuable metric in the design effort. And this open up also the solutions for some neural processing units, which can be combined with AMD or RISC-V as host processors, but we can have this optimized neural processing units in order to further reduce the cost over performance.
I maybe also want to make a small addition to what you, Teresa, mentioned. Like hardware design, often, you know, like we think like we can really optimize the hardware to run very efficiently, etc. But what is often forgotten is to make the hardware software friendly. Like we need to design hardware that is friendly to the compiler and to the entire software stack, such that the average software engineer can basically exploit the benefits of the hardware. If we don't do this, then the hardware can be as efficient as it can be. It will never be used in its most energy efficient modes. And we need to make sure from a hardware perspective that we design it in a way that the software stack can exploit.
Yeah, and in addition to that, if we talk about sustainability, we have to think along the time. So it's not this sustainable or efficient now. So how many times can we use that infrastructure? How adaptable is it? We can, you know, in the future, if we detect that there are another killing application, can we still use that hardware and with tiny modifications on the software or adding little modifications on the hardware, is it still being usable? So we have to think on this long-term perspective. It's not just hardware for now. We have to think, because that's also cost for companies or institutions like EuroHPC. So we have to keep good hardware today, but also for tomorrow problems. Yeah.
Maybe to add on that, Axelera, as said before, like we do a highly customized data path, but we use like also the more general RISC-V capabilities to remain exactly future-proof. One good example is the activation functions, which are changing rapidly, and that's one good example where we need future-proofness, and it's also the job of the hardware to make the hardware sustainable over a long term. Yeah.
That's a very good point. Thank you, Gianna, and thank you, everybody. Let's talk a bit more on a more high level. Let's talk about funding, European funding and collaboration. So, what role does EuroHPC initiatives like the EPI project or DARE or other Horizon Europe grants play in accelerating RISC-V and ARM adoption in Europe? Are we investing enough? Are we doing enough? So what's your point of view? Like Estela, maybe you can start.
Yeah, well, I think the role of the European projects is provide both seed funding for many of these initiatives we see here now on the stage, also visibility to those developments so that there is all motivation for the software developers, the application developers in Europe also to look into, okay, there's new hardware coming up that's coming interesting, let's try and see how we can use it. I think there is a very good start on investments, on different solutions, both on general purpose, both on accelerators, and I really enjoy seeing that there are so many different approaches now here being proposed and being developed. What I really think is always, when you say, is one doing enough? I suppose that the answer is always no, because you can always, or you would always want to have more. But to be honest, I don't think that for me, one of the main problems is not really the volume of funding, which obviously could be higher, but also the long term. So the understanding that this kind of high-end processor technologies, whether however they are being built, whatever is the ISA they are based on, they require years of investment. They require a very deep set of experts that need to grow together as a team, because remember, we are starting from scratch in Europe. So for a couple of decades at least, there was no investment, strategic investment in this area in Europe. And there are a lot of experts in Europe that are working maybe for other companies, but all together as a team working in a European development or several European developments is something that we are starting mostly from scratch. So recognizing that this takes a long time and it requires both the expertise but also the long-term investment and confidence and effort and kind of so resistance in a sense to continue on this, even if it's hard, even if it takes 1, 2, 3 generations until you are really competitive with the others. Realizing how important this is strategically, just looking at the news recently should be made it clear for everybody. I think that this is the time for us to recognize that there is really the need for this long term.
Yes.
And looking at the long term, I think Europe should continue to invest in research and innovation, but even continue to invest in training initiatives like they've done recently for the UMaster for HPC or many EIT digital projects, because of we need to invest to our future, and our future is the young generation, and we need to be very competitive and offering them the best training courses and try to retain and attract our talents in Europe. I think it's very important, the strength of research, innovation and training in Europe.
At EuroHPC, we have recognized that. That's
Exactly.
why we have the pillar of skills and
Exactly.
the pillar of research. So
I think it's fundamental to continue in this direction for our
we basically
future.
we build it from the ground up actually, and
Exactly.
it will take time. Okay,
And, Alexa, if you can, just to be controversial, if you think that is the funding enough, we must say no if we compare with Asia or the US. You know, we have these comparisons that I mean, they are not very good for us. But at the same time, I think we have to highlight the strength that we have in Europe compared to the other continents, and it's this bottom-up approach again. So the innovations, most of the innovation comes from universities, research centers, and then we have these European projects where we can collaborate with the industry, and we can have this nice tandem between academia, industry, and then doing this technology transfer and sharing knowledge. That I think we have to sometimes add value to that, because we don't have to be like others. We have to find our strength and strengthen it more. You know, be different than US. We don't have to be NVIDIA. I mean, we don't need that kind of company here. I mean, we like it, of course. But the thing is that we have to be different. And OpenISO, for example, give us the possibility of doing that. So let's take advantage of that. We don't have to repeat it again and again what others are doing. We don't have to just follow, I don't know, AMD or others. Let's do things different and learn from them, of course. And also learning from other open communities like Linux, for example, on the software side. So I think we are doing, again, a good job. It could be pushed more, but it's very important to have this long-term vision and a strategy, and it's not something that has to be punctual now. It has to be something, it's a long road, and we have to keep pushing to give also alternatives to the young generations. Because if we're training them now, they have to have a job later in the future, and we have to attract talent and retain it, because it's not just let them come, but also stay with us.
Okay. Okay, and to follow up, so basically, you believe that this collaboration, European context between research, academia, and industry, and this technology transfer that naturally happens, gives the competitive edge in Europe compared to US and China.
Yes, but we need to push further. I think, especially from the side of the company, they should invest in the research a little bit more in order to be competitive, especially with the US market, where the presence of funding is very strong in the academia, but in the industry. Companies are investing a little bit more on research than in the European companies, and so I strongly believe that that is a joint effort between the companies and the excellent academic units and research center we have in Europe. So the collaborative approach is very good, and it is our point of effort, but we need to strongly convince our companies in Europe. Why not have the new NVIDIA-like
so
company investing on the AI for the future, and so why not?
And also we have to bridge the gap between pure research, because we have a different mindset, and I think when we are working on these European projects, collaborating with the industry, we are, closing that gap, because industry have the expertise and they really know what their users need. As researchers, we have these great ideas and we think, hey, we want to explore this, let's go for it. But then, where are we going to use this? Let's look for the end application in the end. And the companies do just the opposite. So they have a pain, they want to solve the pain, and we have to, with these collaborations, we have to close this gap. So trying to kind of co-design between industry and research, to be more flexible. But we are doing good steps, and we are going in that direction. That's my perception, at least.
Okay, but still we need to push a bit industry to dare to collaborate a bit more with research, and research try to be a bit more realistic towards more real cases.
Yeah,
and
exactly.
Find
so
a balance.
for example, having PhD programs, industrial programs for PhD could be another step that we could, promote in Europe, because, again, help us to align a mindset between research and industry.
Yeah. Okay.
We need to invest in very strong exploitation plans for our research, I think, with the idea to have a very important impact in terms of European innovation in the future, I think.
Okay. Strong focus on IP, on the technology transfer.
Technology transfer, exploitation, and innovation as well.
Okay.
And also impact, because we can make that transfer, or we can create a lot of patents because we are very good being crazy, but then what do we do with that? So who is going to exploit it? How, the revenues of those exploitations, so it's been used, or, so trying to be more realistic.
Okay, fantastic. Thank you very much. So, and let's talk a bit, since we're talking about technology transfer, let's talk a bit about commercialization. So beyond HPC centers, what do you think are opportunities for European designed RISC-V and ARM technologies in AI, cloud computing, edge computing? So maybe Estela can discuss from SiPEARL.
So, well, I think that the natural other field is data center. So whether they are public or private data centers, so there are growing European data centers that should be also interested on European processor technologies. In the particular case of ARM, there is the market evolution seems to be growing on the amount of ARM CPUs and ARM processors that you see on data centers in general, international. You see this with Graviton was mentioned before, but also there are other developments coming up. So that's a place where also we have an opportunity, I think. So that's a place where we could have, with the European ARM development, a place in this kind of market. Looking now on the AI factories and on the gigafactories and all the factories that are coming up. So that's also an opportunity, maybe also for accelerators, which are kind of the natural as well option. Yeah, so I think that there are places. In our case, in the case of SiPEARL, so this is a server CPU, so we are mostly interested on HPC, data center, cloud market. I know that for Axelera there are other options you are looking for.
Yeah, I mean, we have right now a product that comes to the market that is focused really on the edge. And we want to expand to other market segments as well. That's why the Titania chiplet, which we do within there, we want to really bring to customers in to build their own data centers. So not only HPC, but really also more on-premise data centers, etc. So we're really looking to serve the entire range of markets. And yeah, that's thanks to our technology that is scalable.
Okay, thank you very much. And just since we're running a bit out of time, I want to ask a very short question. So it's about skills. Since most of you interact with students and young researchers, or some of you are a young researcher, can you please tell me if there is still a specific skill gap that is required for the workforce?
I strongly believe we need to invest a little bit more on multidisciplinarity. I mean, students must have skills in computer architectures, but even in specific domains, parallel computing, machine learning. So I strongly believe that we need a really joint view of the problems from the point of view of hardware, software, and acceleration in terms of AI. So multidisciplinarity is my key.
Not easy.
Not easy, but...
For me, it's actually getting more and more low-level software development. So I have the impression that the students nowadays are learning much more high-level languages like Python and other abstractions layers. Now, who are going to be developing and working on the Linux kernel of the next generation? Who is going to be working on the whole low layer of the software stack that we all rely on? So looking in 20 years from now, I really wonder. I think that we are creating, or we are starting to get a gap there.
Yeah.
Yeah, we see a little bit also that challenge. I mean, many students comment they know a lot about AI, Python, etc. But as soon as it's like, really like, since we're really in this specialized domain, understanding the hardware architecture, or then not only the traditional processor computer architecture, but really optimized hardware accelerator, knowing, for example, compiler, as mentioned before, a little bit doing co-design, making the hardware software friendly, and then implementing on a lower level applications, optimized kernels, etc., compiler design. So it's really the full range where we need to strengthen education.
Okay, thank you.
Yeah. Thank you. For me, it's once again about tools, because behind every chip, every design, there are tools. Even if the tools are a little bit the backstage, let's say, because we are talking about the results, the HPC, the IA, so the chips are materials that you can show, you can discuss about, but the tools are also an important part, and we really need multidisciplinarity. We also need to put our hand on it, so we need to motivate students and also professors, researchers to continue developing and put your hand on the tools, and don't forget that are important also to pursue and to ensure sovereignty once again.
Yeah, and we are looking for sovereignty. I think open EVA tools, for example, it's an important piece here. And I'm moving to hardware again, because, for example, we need people on microelectronics, but also interdisciplinary. So photonics, for example, backend tools. For example, now we are working on the design flow. We are lacking of verification people, for example. We don't have that expertise in Europe, and we have to keep pushing and make it visible that hardware is important, because software, I think people is more, I don't know, it's easier to convince young people to use it because they have results very quickly, but when they have to move to hardware, it's like a pain, and they are not used to get results in the long term, so we need to continue pushing in that direction and making more visible and getting more talented people on those kind of things.
Okay. I should have asked what skills we don't need, but we covered, I think, the whole spectrum of what we need. So with this note, I would like to thank you, my panelists.
Thank you.
And please stay on stage, because now I'm going to invite our last keynote speaker. So the last keynote speaker is Jean-Pierre Pansiero from Eviden. And Jean-Pierre is the Chief Technology Officer for HPC at Eviden. And he joined Bull in 2009 and is responsible for the development of HPC and AI high-end systems. After a couple of startups in the Silicon Valley, he worked for 20 years at CGI, first as an HPC application specialist and then as a chief engineer. He's a chairman of ETP for HPC and a member of the EuroHPC governing board. Jean-Pierre, the floor is yours.
Thank you. Thank you very much, Alexia. Thank you very much, the panel. You did a great job. Because, well, I was, I proposed this topic, post-exascale system and the challenges, but when we were preparing this, I realized that we had a couple more challenges. I had a couple more challenges. The first one is time. For such a vast topic, only 12, 15 minutes, that's what I'm given. But the panel did a great job, so I think I will just be repeating most of what was said by the panel. Thank you very much. The second topic, the second challenge that I've given is when we were preparing, I learned that half of the attendance is non-technical. So I don't know if this is this half or this half, but I don't know, but I can do my best there to relay some of the challenges and the topics that we're working on and that need to be addressed. It's not moving. Okay, now it is. So I start with a disclaimer, right? Making prediction is difficult, especially about the future. You heard that, and this is even more true for HPC, HAI, and quantum. Just without going too far back, just if you remember the petascale, the Praise Tier 0 in 2011, they were, were made with 10,000 CPUs, and they were using only 2 megawatts. The pre-exascale that were installed in 21, there are thousands of CPUs as well, but many more GPUs. And, well, they were using much more power, obviously. But at the time, we were still debating, how big the GPU partition should be, or how small it would be, because the application, people were saying that the application wouldn't be there. This is... Okay, this concern got away with exascale, because now you see that this is a staging of the first exascale system in Europe, Jupiter, and you see that there's a lot of GPUs, mostly GPUs, and that's going to use a lot of power. And that's, one good reason for that is because we've seen the AI. Now, AI, and that's something that we've seen a lot, that's changed a lot of things in our industry. And, it's a complete sea change, and this comes from, just a few milestones here. Back in 2015, the AlphaGo here with AI managed to beat the top professional players of Go, the Kasparov of Go. And this was, at least 10, 15 years before everyone had predicted in 2005, given what we knew about technology and the complexity of the game. We also had the surrogate models, and this is something that suddenly we started accelerating our application with that. It's moving along. And then in 2020, AlphaFold, which actually might have gotten a notice at the time because of the COVID, but actually received this year the Nobel Prize. We had the weather forecast. Also something that now we apply AI to many different applications. And so weather forecast, for example, is one that is been using a lot of CPUs and now is working very well with AI. And not to forget all the large and language models. You see the Bloom, the ChatGPT, that everyone, even the non-technical people, are aware of. So all of this has changed a lot. I don't do anything, it's moving. Okay, all of this has done a lot of to change the application. And it's now, with AI, we have a tool now to not only help for innovation, not only accelerate for innovation, but also potentially with universal artificial, what I call universal artificial intelligence, to really drive and generate, innovation. And so it could be, discovering new materials, or designing a friendly plane or eco-friendly plane, finding a vaccine for the next pandemic, or something more rigorous, solving the what's left. The new last Fermat theorems, something that requires a lot of rigor. Then why not design the next European sovereign processor or accelerator? But all of this is something that will require a lot of work so that it can be, before it can be integrated into our application. Not only for the integration itself, using this technology, these techniques, but also in terms of validation and verification. If you remember the Mark Twain quote, beware of health books, you might die of a misprint. You don't want to die of an AI hallucination. So now a little bit about technology. So this chart is just going over the evolution of technology over the last couple of decades. And what we've seen is that there was a sudden change around 2005, the technology kind of hit a wall, a power wall. And what we've seen since then, 2005, so the last 20 years, is that with different technology steps, the number of cores would double in the CPU. So this is a chart for CPUs. But with that, the power consumption was also increased significantly. And so this chart is for CPUs, but with GPUs, they follow the same trend, although at a different design point with much more power used. And when we look at this, I make a prediction for the roadmap for the next 10 years, 15 years until 2036, and you see that there is a plan, an evolution of all the technology, so that we can expect that we'll have more and more resource and more logic in our chips in the future, so at least for the next 10 years. What will we do with this? So the first thing is we can look at this technology, this improvement in the chip technology, microelectronic technology, for the evolution of the current CPUs or GPUs. So it's very probable that we can build a 1,000-core CPU at the time. So this is something in like five years, something like this. But also we can specialize, the accelerators, the GPUs, so that they are more intelligent. More they can be more applied better to AI, and with maybe no more graphic or no more floating points. Or we can build also accelerators, like there was mentioned before, with high bandwidth and large capacity memory. Today we have one or the other, so it would be perfect if we had both. We also could look at disruptive technologies, and just to mention a couple that are coming back often is, for example, you can have what we call processor in memory, so meaning that you can put some logic in the memory device, or even better, stack everything in one 3D stack. People are also looking at neuromorphic processing, so mimicking what's happening in the brain, and the brain, use only, I would say, probably 20 watts, so you have a long way and maybe a lot of potential there. And finally, not to forget the quantum computing. So this is something that will be taking a role in all our future systems. So how do we do, and how do we put this together? We have to connect them, we have to integrate all of them, and, well, yes, we have to cool them because they will be hot. Just if we look at the architecture today, we have this where we put a system. You have, as I said, many accelerators that are there. The accelerators are driven by CPU, hosted with a CPU, and you want to scale up so that your application really goes faster. And, well, you have, different partitions, and they all, have their own scale-up with a shared memory domain. But you also need to interconnect all these different pods. That's how they call. Maybe a pod is a rack mostly, and so you want to connect this because you want to have, hundreds of these pods in your system. So this is what the scale-out, and sometimes east-west because it goes from left to right. But you also need, to connect all of this in your system and have a global network. So that's the north-south, sometimes it's referred to, and connect, with your data lake and all of the rest of the world. And so at this point, I want to mention, and it's been touched on, one of the EuroHPC project, an innovation, Net4Exa, which is actually leading to a product that will be deployable at scale next year for scale-out interconnect. Now, if we talk about how we put this together, there is one thing that was already mentioned, and I think it's very important, is we need the standards for the interface, standard protocols, and standard specifications, standards everywhere. That has to be, that's very important if you want to build efficient processor accelerators. And right now, they're not built in one single die. There are actually multiple die that are accelerated. I mean, this is a trend. And for this, there is one standard that's been proposed, UCIe. It's a Universal Chiplet Interconnect Express. You're all familiar with PCI and interface and the CXL protocol. But we also, I mentioned the using the accelerators. So you have this Ultra Accelerator Link protocol that has been proposed, and that will do the scale-up, and the Ultra Ethernet for the scale-out network. So, and finally, when you put all of this together, the mechanical, electrical specification is something that you could follow with the Open Compute project. So standard is very key to making all of this work together. Finally, I think we mentioned that all these systems are very hot. And I think it was already mentioned a couple of times, you have people that are really excited about gigafactories. And these gigafactories, what I understand at the moment, is that they will be very big, huge, talking about 100,000 GPUs. And each of the GPU being 1.5, 2 kilowatts, And so altogether, that at least 150 megawatt, maybe 300 megawatt. And that's, the power consumption, just to give you an idea, of a small nuclear plant. So what you do, how do you spot a nuclear plant in the landscape? One big cooling tower. How do you spot a gigafactory in the landscape? 2 cooling towers. That's going to be very interesting. Just on another point, a room like this, you can warm it even a cool day like today with maybe 50, 100 GPUs. If you put 100,000 of them, 1,000 times more, would be roasted in a second, and your whole data center will just melt down. So this is something that really needs to be taken into account when you build your own system. And so here I'm reaching the final slide, almost in time. And so the post-exascale challenges that we are facing, to summarize them, first, application. We need to understand what the new set of application will be, and they will integrate a lot of AI, and we have to make sure that we understand what they are, because the hardware that we'll be building and integrating will have to follow that. Second point, very important to me, is the fact that it will be an heterogeneous computing, that it won't be, something very simple. You will have to assemble different partitions, different modules, and they may feature different type of computing elements. And finally, all of this is only possible because, we have limited means. If we collaborate together, if we have all these projects collaborate together, and that's done with the standard building blocks. And finally, these data centers, I think we need to think again how we can build them and really, probably make them new and make sure that they work together, all together. And well, that was my last slide in time. But just, one final, I was asked to put one final exciting announcement, a short one. And well, I won't sing, you know the song, I Love Paris in the Fall. Well, you'll all love Paris, October 6 and 7 for the API Forum. That was the announcement. Thank you.
Thank you, Jean-Pierre, and respecting the time in this amazing way, exactly on 1 second left. Fantastic. So we are the last thing that stops you from the lunch. So I would like to invite Carlos on stage, and we can have a small Q&A. So please let us know if you have any questions. Yes, Harvik.
Thank you very much for this exciting panel. I really enjoyed it. My name is Hartwig Ganz. I'm Chair of Computational Mathematics at TU Munich. And maybe I also want to relate a little bit to the previous panel. So all my PhD students and postdocs, they don't leave Europe. So that is, in terms of retention, they're not moving away from Europe. They're just starting to work for NVIDIA, AMD, Intel, ARM, and so on. One of them actually is working for AVD, but the rest, they are working for the big US companies. And this is not because they want to go there, but it's very difficult for them to see a way to move into this development here in Europe. And in general, I think we should retain them and try to excite them, because currently they're building the math libraries, QSPARS, QBLAS, and so on for the big vendors. Maybe they should rather do that for the European processor. And I think what we are doing is good, but I think we can do really better. And I want to talk a little bit about a previous project that I was part of, the US XSK Computing project, and learn from their mistakes and the things they did right there. So in ECP in 2017, they laid out a roadmap that they will have coprocessors or GPUs from Intel, AMD, and NVIDIA. Except for NVIDIA, it was totally unclear how GPUs from Intel and maybe also AMD looked like. That was very, very unclear. But from the beginning on, it was like, yeah, okay, plan for that. It will be there somehow. And then what they had is, over the duration of the project, they had dungeon sessions where the hardware developers and the software developers got together. They had blueprints, they had simulators, such that the software people could already get a feeling of how these architectures might look like, and they can start developing software for exactly these products. And at the end, when actually the systems hit the ground, the software was there. And I think this is something where we can do better. We are all in the same boat here. We are all working together, and I think we should give up that silo thinking with our personal and individual or institution-wide preferences and interests, and we should really work together on making this happen. And I think maybe there exists something like dungeon sessions that are across all COEs. I wouldn't have heard of it, and I think we can really do better by doing things like that. Thank you.
No question, but okay. Does anybody have a question? Thank you, Harvik, but there was no questions. Yes, there.
So while they are searching for the next question, so there have been some, so there are some activities in this direction. For example, in the EPI project, there are some activities for looking into the emulators and the simulators we have of the hardware. So you should, I mean, I agree that they could be more widely known, and maybe we have to do more to promote them, but these kind of activities do exist. They need to be maybe more announced. That's something we can take as a, as a task.
It was exactly my last word. Tools are behind the scene and not up to the stage, but yeah, we need to encourage that a little bit more maybe.
Okay. And one last question. Yes, please.
Hello.
Hi.
Thank you for the interesting panel discussion. So my name is Mark Doctor. I'm working for Advanced Computing Austria, the company behind the EuroHPC Austria project and the Austrian AI Factory. So the success of GPU was in part because everyone had a GPU in their gaming PCs, and developers and researchers could buy them for 200 euros and up. And only then they started to become expensive. Now they cost like the price of a mid-sized car. but still I can use my CUDA knowledge that I gained from these cheap devices to program on a supercomputer. So what's your plans on getting these accelerators out to developers and into student labs that everyone can kind of get the knowledge to use these super devices that you're promoting? Thank you.
Yeah, so to accelerate, it's really important to make our hardware available to everyone. So we already talked internally also about how we can enable university programs. What I can say already, we have already a web shop on our website to sell and distribute our hardware to a broader community, let's say. But it all takes a little bit of time and work, but know that we are aware of it and we're talking also internally about it.
I think that's also something very interesting is working on RISC-V. There are many people working in open source, their developments, and I think many, or at least some institutions are using that material to incorporate it in the university, in the labs. So I think connecting also with the previous comment, I think we could do like kind of camps to make that available to the people to start playing and understanding how things work. But also on the European projects, we are having also emulation platforms. So at least with MIB, the idea was to create this digital laboratory based on FPGAs. So you get access to early designs before being prototyped or in silicon. So that enables also software people to start using it. So it's just to connect with the people and probably also doing a better job on our side to announce it and make it more accessible. But I think there are mechanisms we have to refine how to make that possible and talk and enable that.
Yes. Okay, thank you. So with this, we can close this plenary. So thank you for your participation. It's time for lunch break. Please don't forget to visit the demo lab. The EPI team is there to showcase the EPAC accelerator. And please thank the panelists and the speakers. Thank you very much. We will be back at 2 p.m. with the parallel sessions. Please stay to take a picture.